Welcome to this deep dive brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are exploring one of the most foundational ideas in modern physics, the photoelectric effect. From Unit 11, Dual Nature of Radiation and Matter. Our mission is to just cut through all the complexity and give you a really solid exam-ready understanding of why light sometimes behaves less like a wave and more like a stream of tiny bullets. Let's start with a simple question for you. Imagine you're trying to move a very large, heavy block, let's say a sofa. What do you think matters more? The total force you apply over time, or the strength and speed of each individual push you give it?
Logically, I'd say the total force, right? If I keep pushing, even if my pushes are a bit weak, eventually the energy should add up and the sofa should move. That just seems logical.
Exactly. And that's precisely what the old rules of physics, classical physics, predicted for light as well. But when we actually look at nature, we find something very surprising. Think about the sun. It is incredibly bright, flooding the Earth with a huge amount of light energy. But only one specific part of that sunlight, the faint ultraviolet light, the UV light, is what actually causes sunburn.
Wait, so you're saying a very bright red lamp, even if it's producing hundreds of times more total energy than a weak UV bulb, it can't cause a sunburn?
Not at all, no matter how long you stand there. The energy transfer depends on the type of light, its color or frequency, not on how bright or intense it is. And this surprising fact is the entire reason we need to understand the photoelectric effect. So the core idea of the photoelectric effect is that light and matter, they just refuse to behave according to the old rules. We found that a single, faint purple lamp, which has a high frequency, can instantly eject electrons from a metal surface. Instantly. But a really bright red lamp, which has a low frequency, cannot eject any electrons, not a single one, no matter how bright you make it. This is the phenomenon we need to explain.
So this is a problem because classical physics saw light as just continuous waves.
Exactly. The old wave theory predicted that brighter light, meaning a wave with a larger amplitude, should always transfer more energy. The fact that the color, the frequency, mattered more than the brightness, the intensity, that was a fundamental contradiction. To really get it, let's use an analogy, the concert door. Think of electrons escaping from a metal as guests trying to get into a concert. But the venue has a strict rule, a minimum height requirement. In physics, we call this the work function.
Okay, a minimum height to get in.
Yes. Now, the color of the light, its frequency, that determines the height of each individual person trying to enter. And the brightness of the light, the intensity, that just determines the number of people arriving, the size of the crowd.
Ah, I think I see. So if I have 50 short people, which would be like many low-frequency red photons, none of them can get in because each one individually is below the height requirement.
Precisely. They can't pool their heights together. It's an individual check. But even a single tall person, a high-frequency violet photon, can walk right in. Instantly. Frequency is the gatekeeper, intensity is just the crowd size.
That makes it much clearer. So this minimum height, this work function, does it change for every metal?
That's absolutely correct. The work function, which we write as phi naught or W, is a critical property of the metal itself. It's the minimum energy required to pull an electron out from that specific surface. So for example, cesium has a very low work function, an easy cliff to jump off.
Right.
But platinum has a very high work function, a very tall cliff. Now that we have the mental image, let us see how insert formally defines this.
Okay, I have it here. Reading from insert. Photoelectric emission. When light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. These photolight-generated electrons are called photoelectrons. The phenomenon is called the photoelectric effect.
Good. The key phrase there, the most important one, is suitable frequency. That one phrase is where all the old physics failed, and that's what Einstein explained in 1905. He proposed that light is made of these discrete energy packets called, quanta, or as we now call them, photons. Let's break down his explanation into a few steps. It's very logical. Step 1. Each photon carries an energy given by the formula E equals h nu, where h is Planck's constant and nu is the frequency. This means energy is determined by frequency, its color, and not its brightness. Step 2. When a photon hits an electron, it's a one-to-one collision. It's all or nothing. The photon transfers all its energy, h nu, to that electron, and it does it instantaneously. There's no delay.
Okay, so the electron gets all that energy at once. What does it do with it?
Good question. That's step 3. The electron first has to use a part of that energy just to escape the metal. That minimum energy needed to escape is the work function, phi naught, whatever energy is left over. That becomes the electron's maximum kinetic energy. It's energy of motion, Kmax. And this gives us Einstein's photoelectric equation, which is so important for your exams. Kmax equals h nu minus phi naught.
The energy it leaves with is the energy it got minus the cost of leaving.
Perfect. That's the perfect way to say it. And that leads to step 4. For an electron to be emitted at all, its kinetic energy, Kmax, has to be 0 or positive, isn't it? It can't be negative.
Right, that wouldn't make sense.
So that means h nu must be greater than or equal to phi naught. This simple condition defines the minimum frequency required for emission. We call it the threshold frequency, naught. If your light's frequency is less than this threshold, no emission happens, period. Even if the light is blindingly bright. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Let's use a very simple example to see how this works practically. Suppose cesium metal has a work function, phi naught, of 2.14 electron volts, and we shine light on it where each photon has an energy, h nu, of 2.74 electron volts. What's the maximum kinetic energy of the ejected electron?
Okay, so we use the equation. Kmax is h nu minus phi naught. So that would be 2.74 eV minus 2.14 eV, which is 0.60 eV.
Excellent. Now, what does this maximum kinetic energy mean in terms of stopping these electrons? Experimentally, we can measure this. We know that Kmax is also equal to E times V naught, where V naught is the stopping potential.
So since Kmax is 0.60 electron volts, the voltage we need to apply to stop even the fastest electrons, that must be 0.60 volts.
Exactly. It's that direct. This simple calculation shows the link between the light's frequency, the metal's property, and the resulting electron speed. In understanding this instantaneous quantized interaction of light with matter, it completely changes our view. It forces us to accept that light has a particle nature. And this leads directly to our next big idea. The dual nature is universal. If light, a wave, can be a particle,
Then maybe a particle like an electron can be a wave?
that is the bold hypothesis proposed by de Broglie. It follows right from this. Now let's switch gears and address the silent killers. The misconceptions that often cost students marks in the exam. Misconception number 1. A lot of students think that the maximum kinetic energy, Kmax, increases if we increase the intensity of the light.
Because brighter light just feels more powerful, I suppose.
It does. But it's wrong. The correct idea is that Kmax depends only on the frequency. It's in the equation. Kmax equals h nu minus phi naught. It is completely independent of intensity. So here's the hook to remember. Intensity controls how many electrons are ejected, which is the current. Electron is.
Okay, I need to remember that. Intensity is about the number of electrons, the photocurrent. Frequency is about the energy of the fastest ones, the Kmax.
Precisely. That is the key distinction. Now for the second misconception. Many think that all ejected electrons have the exact same kinetic energy, Kmax.
Because the equation just gives one value, right?
Yes, but that value is the maximum. It's only for the electrons that are ejected from the very surface without losing any energy on the way out. Electrons from deeper inside the metal, they might lose some energy to collisions before they escape, so their kinetic energy will be less than Kmax.
So the energies are actually in a range from 0 up to Kmax, and the stopping potential, V naught, it measures the Kmax because it has to stop the very fastest ones.
You've got it. It's designed to stop the fastest champions, not the stragglers. And the third one, which is really dangerous, it goes back to our first question. Students think if the frequency is below the threshold, you can still get emission if you just use very bright light and wait for a long time.
That's the old classical idea of energy accumulating over time.
Yes, but the quantum truth is that photoelectric emission is instantaneous. It's a one-to-one event. If one photon doesn't have enough energy, h nu, to overcome the work function, then no emission occurs. Waiting longer or adding more photons doesn't help.
So the frequency must unlock the gate. Intensity can't force it open.
That is the ultimate summary. Perfect. Now, to anchor this for your exams, let's use some memory hooks. First, the formula itself. H-U equals W plus KE. You can say it as a sentence. Photon gives work plus kinetic energy.
Photon gives work plus kinetic energy.
The best summary phrase to remember is, frequency unlocks the gate. Intensity determines the flow. And finally, a physical gesture. To visualize Kmax equals h nu minus W. Hold one hand high for h nu, the input energy. Bring your other hand up to your chest level, that's W, the barrier, the gap that remains between your hands. That is the leftover energy, the Kmax. It's a physical reminder that the input has to be higher than the barrier. All right, to summarize this entire deep dive, here are 3 exam-safe factual points. Number 1, light energy is quantized. It comes in discrete packets called photons, where the energy E equals h nu depends linearly on its frequency. Number 2, photoelectric emission needs the photon energy h nu to be more than the work function phi naught. This creates a sharp threshold frequency. Below it, nothing happens. And number 3, the maximum kinetic energy of the photoelectrons is given by Einstein's equation, Kmax equals h nu minus c naught. It increases with frequency and is crucially independent of light intensity. To get maximum marks in 12 CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is Prof Sam, right?
Yes, ProfSam.com. Study hard and all the best for your exams.